we have all of these algebraic properties for matrices, and one thing that this lets us do is do algebra with matrices. For example, we could try to simplify a matrix expression like this. So let's assume that all of the operations in this expression are actually defined, which means that well, let's not worry about what it means, I guess. Maybe at the end we can interpret what it means about the sizes of a and b. But assuming that all of these operations are defined, let's simplify this. So we have a squared, and remember, squaring is just multiplying by itself. So a plus b squared is a plus b times a plus b. Okay. And, well, how to multiply this out? Well, we can't just, FOIL it out, because that actually assumes we have commutativity. And we don't have commutativity with matrix multiplication. So I guess we need to distribute. So let's distribute this way. So we get a times b plus a times a plus b plus b times a plus b. Okay, now we can distribute the other way like this. So we get a, b, plus a times a, which I guess we can call a squared, plus a times b, plus b times a, and then plus b times b, but that's b squared. Okay. And now we have two copies of ab here, so this is 2ab plus a squared plus ba plus b squared. Now you see what the real difference with matrices is compared to algebra with real variables. For matrices, we can't assume that a times b and b times a are equal. So whenever we do a product or a distribution like this, we have to keep the products in the order that they're actually in. We can't freely switch the order of a times b, because there's no guarantee that a times b is equal to b times a. So we have to leave things in the order in which they appear. We can't turn this b times a around. So careful with matrix multiplication. Let's look at one more example of doing some algebra. Oh, I guess I said that we would look at the sizes. Well, a is m by n. And so for this matrix product to be defined, b had better be n by something. Okay, so right there, these inside sizes have to match. All right, so what about this one? Well, b is n by p, and a is m by n. But for this to be defined, these sizes had better match. So p had actually better be equal to m. So instead of p, let's write m, since they must be equal. So far, b is n by p, which is really m by n, and a is m by n. Okay, but look over here. b, we have to be able to multiply b by itself. And b is n by m, and b is n by m. So these inside sizes had better match. So they'd better be equal. So b actually has to be n by n. And the same thing goes for a. Here we have a squared, which is a times a. So this is m by n and m by n. So these inside sizes had better be the same, and so n is equal to m, which I guess we knew before from up here. So a is also n by n. So the only way for this expression to be defined is if a and b are the same size and both square matrices that are the same number of rows as columns. Okay, so let's look at our second example. Let's find the matrix A. Well, look, this is an equation where A is a variable. It's a linear equation in a matrix where A is the variable. So let's just isolate the variable. So we can subtract this matrix from both sides. So that gives us negative 2a equals, and now I'm going to subtract these two matrices. So it's this matrix on the right minus the matrix that shows up on the left. So, and to do matrix subtraction, that's just entry by entry. So 7 minus 1 is 6, 3 minus negative 5 is 8, and then minus 1 minus 9 is negative 10, 2 minus 4 is negative 2, 0 minus negative 4 is positive 4, 4 minus 6 is negative 2, minus 3 minus negative 3 is 0, 5 minus 3 is 2, and then 1 minus 7 is negative 6. Okay, and now divide by minus 2. Right, so we get a equals minus 1/2 times this whole matrix. And we can do this scalar multiplication. You see all these entries turned out to be negative, or turned out to be even, so dividing by 2 is actually nice. It's almost as if someone arranged for all of these numbers to come out to be even. So 6 times minus 1/2 is negative 3, and then negative 4, positive 5, positive 1, negative 2, positive 1, 0, negative 1, and 3. So there's our matrix A. So you can see now that we have these matrix operations, and we also have, we know all of the algebraic properties that they follow, we can actually do genuine algebra with matrices.